Summer of 1944, Rechlin Test Facility, Germany. Oberingenieur Klaus Hartmann stands in Hangar 7, staring at an aircraft that should not exist here. North American P-51 Mustang, serial number 42-103458, coded T9 plus CK in Luftwaffe markings, the entire underside painted bright yellow for identification. Captured intact after Lieutenant Thomas Fraser force-landed near the Hungarian border due to weather. Hartmann has spent the last 3 hours examining the Packard V1650 Merlin engine. He holds the maintenance log pulled from the aircraft. Total engine time, 247 hours. No major overhaul, no cylinder replacement, just routine oil changes and spark plug maintenance. He reads the entry again. 247 hours. His hand trembles slightly. In the Luftwaffe, a Daimler-Benz DB605 averages 100 to 120 hours before mandatory teardown. The best engines, pampered by expert mechanics, might reach 180. This American engine has flown nearly double that time, and the internals, according to the inspection report on his clipboard, show minimal wear. Hartmann turns to his assistant, Lieutenant Dieter Krebs. This cannot be correct. Check the log again. Perhaps the Americans record flight hours differently. Krebs shakes his head. Already verified, Herr Oberingenieur. The calculations are accurate. Engine hours, not aircraft hours. He pauses. There is more. According to the technical intelligence from captured American maintenance records, their specified overhaul interval is 300 hours. Not 100, 300. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The statement hangs in the air between them like an accusation. Hartmann has designed engines for 8 years. He helped develop improvements for the DB601. He knows what is possible and what is fantasy. 300 hours between overhauls violates everything German engineering understands about internal combustion engines operating at combat power levels. Prepare the test stand, Hartmann says quietly. We run this engine until it fails. I need to understand what they have done. But what Hartmann is about to discover will challenge not just technical assumptions, but the entire philosophy that German industry has followed since the days of Benz and Daimler. The Americans have not built a better engine through precision, they have built a better engine by abandoning it. When people remember the air war over Europe, they speak of courage and tactics, of fighters dueling at altitude, of bomber formations darkening the sky. But wars are decided not only by the men who fly, but by the machines that keep flying. The P-51 Mustang became the fighter that broke the Luftwaffe's back, not because it was faster, though it was, not because it had longer range, though it did, but because its engine refused to die. This is the story of how reliability defeated precision, how mass production philosophy conquered craftsman tradition, how an American engine that German engineers called crude outlasted everything the Third Reich could build, and how one detail, invisible from the cockpit, determined which nation would control the skies. October 1940, Packard Motor Car Company, Detroit, Michigan. The conference room on the 3rd floor overlooks the assembly lines. 13 men sit around a mahogany table. On one side, 3 engineers from Rolls-Royce, freshly arrived from Britain. On the other, Packard's engineering staff, led by Chief Engineer George Christopher. The British have brought blueprints. 427 pages of technical drawings for the Rolls-Royce Merlin engine, tolerances specified to within 1/1000th of an inch, assembly procedures that require hand selection of parts, a list of specialized tools, many custom-built for specific operations. Christopher examines the drawings with increasing concern. He's 52 years old. He learned manufacturing under Henry Ford himself. He has spent 30 years turning complicated machines into products that ordinary workers can build in quantity. The Merlin, he sees immediately, is not designed for mass production. It is designed for craftsmen. Ronald Harker, Rolls-Royce's senior test pilot and liaison, explains the process. Pistons are individually weighed and matched to within 0.5 grams. Connecting rods are balanced as sets. Main bearings are hand-fitted to each crankshaft. The crankshaft itself requires 16 hours of balancing and alignment. How many engines does this process produce per month? Christopher asks. Derby produces approximately 400. Crewe and Glasgow combined, another 460. We are expanding to Manchester. Christopher does quick mental arithmetic. Britain needs thousands of engines. The United States will need thousands more if they enter the war. Current Rolls-Royce production is nowhere near sufficient. What is your rejection rate? Harker hesitates. Approximately 11% fail initial testing. Another 8 to 9% require rework during assembly. Christopher makes a note. 20% of engines need corrective action. That means the actual output is even lower than stated. He looks at his lead production engineer, Malcolm Hodges. Hodges is already shaking his head. We need to discuss modifications, Christopher says carefully. The Rolls-Royce men stiffen. Stanley Hooker, their chief engineer, speaks for the first time. The Merlin is the finest aircraft engine in the world. It powers the Spitfire. It will power the next generation of RAF fighters. Every specification has been developed through exhaustive testing. I do not question the design, Christopher responds. I question whether it can be manufactured at the scale required to win a war. The meeting grows tense. The British see the Merlin as a precision instrument, a marvel of engineering. The Americans see a production nightmare. Hand-fitting, custom tools, processes that require skilled machinists rather than assembly line workers. Hodges speaks up. Let me be direct. Packard builds automobile engines. Last year we produced 87,000 straight-eight engines. The year before, 94,000. We do not hand-fit parts. We do not balance components individually. We machine to consistent tolerances, and we interchange any part with any engine. That is exactly what concerns us, Hooker says. The Merlin requires precision. The Merlin requires reliability, Christopher counters, and reliability at scale requires standardization. The argument continues for 2 hours. Finally, a compromise emerges. Packard will build the Merlin to Rolls-Royce specifications initially, but Packard will be permitted to propose modifications that maintain performance while improving manufacturability. Rolls-Royce will review each change. It is an uneasy piece. The British fear American cowboys will ruin their masterpiece. The Americans fear British perfectionism will make mass production impossible. Neither side yet understands that this tension, this philosophical clash, will produce an engine superior to either approach alone. January 1941. Packard plant, Detroit. The first Merlin V1651 runs on a test stand, outwardly identical to its British cousin. Internally, subtly different. Hodges walks Christopher through the changes. Main bearings. Rolls-Royce uses copper-lead alloy, requires hand-fitting to each crankshaft. We switched to silver-lead with indium plating. Harder surface, better load distribution, and it does not require fitting. Any bearing fits any crank within tolerance. Christopher examines the bearing. Performance? Actually better. Break-in time reduced by 30%. Load carrying capacity increased approximately 15%. The British approved this. After testing, their initial reaction was negative. Then their test data matched ours. They moved to the supercharger assembly. This is the big one, Hodges says. Rolls-Royce uses a French Farman design. Two-speed, mechanically shifted, complex, prone to failure under stress. We licensed a Wright aeronautical epicyclic design instead. Simpler mechanism, more reliable shifting, smoother power delivery. And Rolls-Royce opposed it for 6 months, then tested it. Now they want us to retrofit British engines. The pattern repeats across dozens of components. Packard engineers trained in automobile mass production systematically eliminate hand-fitting operations. They widen tolerances where it does not affect performance. They standardize parts that Rolls-Royce built custom. They choose durability over theoretical efficiency. The British engineers reviewing each change grow increasingly frustrated. These Americans are making their beautiful engine crude. But the numbers tell a different story. By June 1942, Packard produces 700 engines per month. By December, 1,050. Rejection rates drop to 4%. Assembly time falls from 42 hours to 26 hours. And something unexpected happens. The engines last longer. Rolls-Royce specified 240 hours between major overhauls for fighter applications. Packard-built engines consistently exceed this. Field reports from early P-51Bs show engines reaching 280, 300, even 320 hours before requiring teardown. The secret is not in precision. It is in forgiveness. German engineers, like their British counterparts, chase theoretical perfection, tighter tolerances, more precise machining, components matched to exact specifications. The result is engines that perform brilliantly when new, when assembled correctly, when maintained by experts. But war does not provide ideal conditions. Mechanics work in mud and rain. Replacement parts come from different production batches. Filters clog with dust. Oil specifications change. Fuel quality varies. Temperature swings from -20 to +40 Celsius. A precision engine fails under imperfect conditions. Its tight tolerances become liability. A grain of sand jams a piston. Thermal expansion binds a bearing. A slightly incorrect oil viscosity starves lubrication. Packard builds forgiveness into every dimension. Piston clearances slightly wider, bearing surfaces slightly thicker, oil passages slightly larger. To a German engineer examining the blueprints, it looks wasteful, inefficient, but in actual operation, those wider clearances let dust particles pass through without scoring cylinder walls. Those thicker bearings tolerate marginal lubrication. Those larger oil passages maintain flow when the oil thickens in cold weather. Christopher's team does not set out to build a more reliable engine. They set out to build an engine that can be manufactured by ordinary workers and maintained by ordinary mechanics. Reliability emerges as a side effect of that philosophy. March 1943, RAF Duxford, England. Squadron leader James Lynch walks around his new P-51B. After 2 years flying Spitfires powered by Rolls-Royce Merlins, he is curious about the American version. His crew chief, Sergeant Peter Mills, is performing the pre-flight inspection. Lynch watches him work. Mills is 21 years old. Before the war, he repaired motorcycles. 6 weeks of training qualified him to maintain fighter aircraft. "How does the Packard compare to the Rolls-Royce?" Lynch asks. Mills straightens up, wiping his hands. "Easier, sir, much easier. The Spitfire, if we had an oil pressure issue, it usually meant bearings. Had to pull the engine, ship it back to the depot. Could be a week before we got a replacement. This?" He taps the Mustang's cowling. Oil pressure drops. 9 times out of 10, it's just the oil. Change it. Reset the filter. Back in the air. And if it is the bearings? Still easier. Americans design their engines for replacement, not repair. We can swap the whole power plant in 14 hours with a good crew. The Rolls-Royce took 24 hours minimum. Lynch considers this. But the Rolls-Royce Merlin is more refined, is it not? Smoother. Mills chooses his words carefully. The Rolls-Royce is a beautiful engine, sir. Runs quiet, balanced, lovely piece of work. But this war isn't about beautiful. It's about what works tomorrow after today broke it. Lynch flies the P-51B that afternoon. Mills is right about smoothness. He can feel slightly more vibration than in his Spitfire. But the engine never hesitates. Power comes instantly. Response is crisp. 3 weeks later, Lynch experiences the real difference. Returning from a bomber escort mission over Bremen, his P-51 takes flak damage. A fragment punctures the oil cooler. Pressure begins dropping. He nurses the aircraft back across the channel, landing with the oil temperature at 130 degrees, well into the red zone. Mills inspects the engine the next morning. "Oil's cooked, sir. Bearings took a beating, but..." He rotates the propeller by hand. Still smooth, no scoring. In a Spitfire, this would have seized. They change the oil cooler, flush the system. Fill with fresh oil. The engine runs perfectly. No teardown necessary. No depot maintenance. Mills signs off the aircraft. It flies again that evening. Lynch writes in his logbook, "American engines may lack British refinement, but they have something more valuable. They do not quit." The Luftwaffe notices this pattern. Intelligence reports from interrogated P-51 pilots reveal consistent accounts. American engines rarely fail. When damaged, they continue running. Field repairs that would ground a German aircraft for days take Americans hours. But the Germans misunderstand the cause. They attribute it to inferior enemy standards, looser tolerances, less precision. They believe American engines work despite their crude construction. Not because of it. Klaus Hartmann at Rechlin is about to learn otherwise. June 1944, Rechlin Test Facility. The captured P-51B sits in the test hangar, engine cowling removed. Hartmann supervises a team of 6 mechanics as they prepare the Packard-Merlin for detailed examination. Obergefreiter Ernst Müller, the senior mechanic, completes the initial inspection. He has maintained DB605 engines for 3 years. He knows what a well-made engine looks like. "Herr Oberingenieur," he says slowly, "this is strange." "Strange how?" Müller gestures at the exposed cylinder block. The castings are rough. Machine marks are visible. The surface finish on the crankcase is maybe 8 to 10 microns. Our DB605 is polished to 3 microns. "Sloppy American work," says Lieutenant Krebs dismissively, but Müller is frowning. Yet, there is no oil weeping, no leaks. The gaskets seal perfectly, despite the rough surfaces. Hartmann moves closer. Müller is correct. The Packard engine shows none of the meticulous surface finishing that characterizes German engines. It looks, frankly, crude. Yet it functions flawlessly. They remove the cylinder head from one bank. The combustion chambers show normal carbon deposits. The valves are slightly worn, but well within tolerance. The valve seats, however, catch Hartmann's attention. "The clearances," he says. "Measure them." Müller uses a feeler gauge. 0.4 millimeters, Herr Oberingenieur. Hartmann checks his notes. The DB605 runs 0.15 to 0.2 millimeters. This is nearly double. "Inefficient," Krebs observes. "Compression loss. Reduced power." But Hartmann is thinking. Wider clearances mean less precise machining required, faster production. And if the compression loss is minimal, perhaps acceptable. They continue disassembly. The pistons come out next. Müller weighs each one. Variation of 12 grams across all 12 cylinders. Hartmann's eyebrows rise. 12 grams. That is enormous. The DB605 pistons are matched to within 1 gram. "This engine should shake itself apart," Krebs says. Yet the bearings tell a different story. Hartmann examines them under magnification. Normal wear patterns. No hot spots. No unusual stress. The engine has been running smoothly, despite piston imbalance. That would be unacceptable in German practice. The crankshaft reveals the most surprising finding. Hartmann runs his finger along the bearing journals. "Look at this surface treatment. It is not our copper-lead alloy." "Silver lead," Müller says, examining a bearing with some kind of coating. "Very hard." Hartmann makes notes. The Americans use different bearing materials, harder surfaces, probably less precisely fitted, but more durable. "What is the pattern here?" he asks aloud, not expecting an answer. Everything is looser, cruder, less refined, yet the engine runs reliably for 247 hours. Krebs offers the obvious answer. Perhaps the pilot's logbook was falsified, perhaps American record-keeping is sloppy. But Hartmann shakes his head. The wear patterns are consistent with extended operation, and look at the spark plugs. He holds one up. Properly gapped. Clean electrodes. These have been changed regularly, perhaps every 15 to 20 hours. The maintenance was good. He pieces it together, slowly. The Americans do not hand-fit parts because they do not need to. They build in margin. They accept slightly reduced theoretical efficiency in exchange for practical reliability. They design not for perfect conditions, but for real conditions. It is the opposite of everything Hartmann has been taught. "Set up the test stand," he orders. "We run this engine at full power until we understand its limits." Over the next 3 weeks, Hartmann's team runs the Packard-Merlin through exhaustive testing. They operate it at various power settings, monitor temperatures, measure fuel consumption, analyze vibration. The engine performs consistently, not brilliantly, but steadily. At full power, it produces approximately 1,300 horsepower. The DB605A produces 1,475, a clear German advantage. But then Hartmann notices something in the data. The Packard maintains rated power for extended periods. The DB605, when operated continuously at full power, begins losing performance after 20 minutes. Temperatures rise, oil pressure drops slightly, power output decreases by 5 to 8%. The American engine simply keeps running. "Test the cooling system capacity," Hartmann orders. The results are revealing. The Packard's coolant passages are larger than theoretically necessary. The radiator has excess capacity. The oil cooler is oversized. By German standards, wasteful. In practice, insurance against overheating. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Hartmann writes in his report, "The American engine philosophy appears to be designing for sustained operation rather than peak performance. Thermal management systems are deliberately overspecified. This reduces maximum efficiency, but increases reliability under stress." June 12th, 1944. Rechlin hosts a major exhibition. The latest German prototypes are on display. He-177B5, R-234 jet, Me-262, and, for comparison, captured Allied aircraft. The P-51B with coded T9 plus CK draws considerable attention. Hauptmann Hans-Werner Lerche, Rechlin's chief test pilot, is scheduled to fly the Mustang. He has flown over 100 different aircraft types. He approaches each captured machine with professional curiosity rather than prejudice. Hartmann briefs him on the engine characteristics. "It is less refined than our engines, but quite reliable. Operate it normally. The Americans rate it for continuous operation at 61 inches of manifold pressure." Lerche climbs into the cockpit. The first thing he notices is the instrument layout, more crowded than a Bf-109, more switches and controls. He starts the engine. The Packard-Merlin catches immediately, settles into a steady rumble, definitely rougher than a DB605, more vibration through the airframe. But the response is good. Throttle movement produces instant reaction. Taxiing feels different. The P-51's wide landing gear makes ground handling easier than the Bf-109's narrow track. Takeoff is straightforward. The Mustang accelerates smoothly, lifts off cleanly. Lerche climbs to 6,000 meters. He begins performance testing. Level speed at various power settings. Climb rate. Turning radius. The Mustang handles well. Responsive. Stable. Range, according to American documents, is extraordinary. Over 1,800 kilometers with drop tanks. But what impresses Lerche most is not performance. It is consistency. The engine never varies. Power output remains constant. Temperatures stay in the green. Every control input produces predictable results. He thinks of the Bf-109 G6 he flew yesterday, superior in some specifications, but temperamental. The DB605 requires constant attention. Throttle movements must be smooth. Power changes need anticipation. Push it too hard and it overheats. Run it too lean and it coughs. The Mustang's engine asks nothing. It simply works. After landing, Lerche makes notes for his report. He writes carefully, knowing his assessment will be read by senior Luftwaffe commanders. He must be honest, but he must also be diplomatic. "The P-51B is a formidable aircraft," he writes. "Performance is comparable to our Bf-109G and FW-190A in most regimes. High-altitude performance is excellent. Range is exceptional. But the most significant advantage is not visible in specifications. It is reliability. The engine operates without drama. It tolerates pilot error. It continues functioning under conditions that would distress our power plants." Then he adds a sentence that he knows will be controversial. In combat, the American philosophy of reliable adequacy may prove more effective than our pursuit of maximum performance. Hartmann reads Lerch's report with grim satisfaction. The pilot has reached the same conclusion. But will anyone listen? July 1944, Luftwaffe High Command, Berlin. General Adolf Galland, Inspector of Fighters, reviews technical reports from Rechlin. He reads Hartmann's analysis of the Packard-Merlin. He reads Lerch's flight evaluation. He reads intelligence summaries about P-51 operational readiness rates. The numbers are damning. American P-51 units maintain approximately 85 to 90% aircraft availability. Luftwaffe fighter units, by comparison, struggle to keep 70% operational. And that disparity is growing. Galland calls a meeting with engine manufacturers. Representatives from Daimler-Benz and BMW attend. He presents the Rechlin findings. The Americans build engines that last 300 hours between major overhauls. Galland states, our best engines require overhaul at 220 hours. Our average is 100 to 120. Why? Engineer Friedrich Nallinger from Daimler-Benz responds. The American engines sacrifice precision for durability. Their tolerances are loose. Their surface finishes are inadequate. Their components are not properly balanced. Yet they outlast ours by 2 to 1, Galland says flatly. Quality cannot be measured only in operational hours, Herr General. The DB605 produces more power for its displacement. It is more fuel efficient. It represents superior engineering. Galland's patience snaps. I do not need superior engineering. I need engines that keep my fighters in the air. Can you implement American methods? Nallinger stiffens. The American methods are antithetical to German engineering principles. We cannot simply widen tolerances and hope for the best. Our manufacturing infrastructure, our supply chains, our workforce training, all are built around precision production. Then change them. Herr General, we cannot redesign our entire production system in the middle of a war. Such changes would require months of retooling, production would halt, and there is no guarantee the results would be better. Galland sees the trap. The Germans have committed to a philosophy. Changing course now would cause more disruption than benefit. They must continue with what they have, even knowing it is inferior. Then improve reliability within our current approach, Galland orders. Reduce the complexity. Simplify maintenance. Do whatever is necessary to increase operational availability. Nallinger nods, but both men know it is too late. The American industrial system has been building toward mass production for 40 years, since Henry Ford's assembly line, since interchangeable parts became standard practice. The Germans cannot replicate that infrastructure overnight. Later, Galland writes in his diary, we build Stradivarius violins, the Americans build harmonicas, but in war, you do not need a Stradivarius. You need 1,000 harmonicas. August 1944, 8th Air Force, England. Major Robert Johnson of the 56th Fighter Group completes his 20th mission in P-51D Ridge Runner 3. The aircraft has 218 hours on the engine. No major maintenance issues. Johnson's crew chief, Technical Sergeant Mike Romano, performs the post-flight inspection. Everything is normal. Oil consumption is steady. Spark plugs show proper color. Compression test results are within specification. How much longer on this engine? Johnson asks. Romano checks the log. Scheduled overhaul at 300 hours, so we got another 82 hours, give or take. And if we push it, sir, I've seen these engines go 350, even 400 hours when properly maintained, but officially we swap at 300. Johnson thinks about this. His previous aircraft, a P-47 Thunderbolt, went through 2 engine changes in 6 months. Combat damage both times. But still, the Mustang's Merlin just keeps running. What's the secret? He asks Romano. The sergeant shrugs. Honestly, sir, I think it's that they're designed for idiots like me. I'm not an engineer. I'm a kid from Brooklyn who took a 6-week maintenance course. But Packard built this engine, so a kid from Brooklyn could keep it running. Everything is simple. Everything is accessible. Parts are interchangeable. If something breaks, I swap it. I don't repair it, I replace it. German engines are different. From what I hear, yeah. Their mechanics need to be craftsmen, ours just need to follow the manual. It is a profound observation, though Romano does not realize it. The American system distributes complexity away from the field. Simplify the maintenance, standardize the parts, move the expertise to the factory, not the front line. The result is that a 20-year-old sergeant with minimal training can maintain an engine that performs almost as well as a German engine maintained by an expert with years of experience. And there are thousands of sergeants like Romano, but there are only hundreds of German expert mechanics, and they are working themselves to exhaustion. September 1944, JG 300, Germany. Obergefreiter Karl Schneider works on a Bf 109G6. The DB 605 needs attention. Again, the aircraft returned from this morning's mission with high oil consumption. Schneider has seen this pattern before. It usually means the piston rings are worn, or possibly the cylinder walls are scored, or the valve guides are loose. With a DB 605, it could be many things. He begins the diagnosis. Check oil pressure. Normal. Check for external leaks. None visible. Check blow-by from the crankcase breather. Excessive. Definitely internal wear. This means engine removal. The DB 605 can be unbolted from its mounts and lowered out of the airframe relatively quickly, 30 to 40 minutes, with a good crew. But then comes the teardown. That is where time disappears. Schneider has been doing this for 2 years. He's good at it, but even good mechanics need hours to properly disassemble, inspect, and reassemble a DB 605. And they need weights, parts that are increasingly difficult to obtain. The new pistons he needs are on order. They were supposed to arrive last week. Now he is told maybe next week, maybe the week after. The supply system is breaking down, so Schneider does what mechanics do when they have no choice. He improvises. He takes pistons from a damaged engine in the scrap pile. He cleans them. He measures them. Close enough. Not ideal. The Germans stopped matching pistons precisely to cylinders last year. Cannot afford the time. He rebuilds the engine. It takes 3 days. When he runs it, there is a slight vibration, not terrible, but noticeable. He notes it in the logbook. The pilot will complain. Nothing to be done. The aircraft returns to service. It flies 2 more missions. Then the engine fails catastrophically. A piston seizes. Connecting rod breaks. Crankcase cracks. Total loss. Schneider is not surprised. Mismatched parts plus extended operation at emergency power equals inevitable failure. He writes the report. He requests another engine. He waits. The replacement arrives 11 days later. Used. From another unit. 230 hours on it. Close to overhaul time. But it runs. Schneider installs it. The aircraft returns to service. This is German reliability in late 1944. Not enough new engines, not enough parts, not enough time. Mechanics performing miracles with inadequate resources. Meanwhile, American units swap Packard-Merlins like changing tires. Engine reaches 300 hours. Pull it. Install. Fresh one. Takes 12 to 14 hours. The old engine goes to depot maintenance. Gets completely rebuilt under factory conditions. Returns to the supply system. The American system works because it is designed to work. Abundant engines, standardized parts, clear procedures, well-supplied depots. The German system is collapsing because it depended on conditions that no longer exist. Skilled craftsmen. Adequate materials. Time for proper work. October 1944. Rechlin. Hartmann has been working on his final report for 4 months. It is detailed. It is thorough. It is devastating. He documents the Packard-Merlin's operational life. He compares it to the DB605, the BMW 801, and the Junkers Jumo 213. The Americans lead in every reliability metric, but more importantly, he explains why. He details the American production philosophy, the design margins, the simplified maintenance, the supply chain integration. His conclusion is carefully worded, but the message is clear. German engine development has prioritized maximum performance and engineering excellence. This approach produces superior engines on paper. However, American engine development prioritizes sustained operational availability and field maintainability. In extended operations, the American approach yields superior results. The Packard P-51 1650 Merlin demonstrates that adequate performance, consistently maintained, defeats superior performance, inconsistently available. He recommends immediate changes to German production priorities, widen tolerances, simplify designs, standardize parts, focus on reliability over peak performance. The report reaches Galland's office in November. Galland reads it twice. He understands it completely. He agrees with every conclusion. Then he files it away. It is too late. Germany cannot retool its entire aviation industry. The factories are being bombed, raw materials are scarce, skilled workers are being conscripted. The recommendations are sound, but they require time and resources that no longer exist. The Americans won the engine war not in 1944 when the P-51 dominated the skies. They won it in 1941 when Packard decided to build the Merlin their way instead of the Rolls-Royce way. They won it in 1938 when American industry adopted mass production principles that made adequate performance available in unlimited quantities. By the time Hartmann's report is filed, 20,000 P-51 Mustangs are flying with Packard-Merlins. Their engines are lasting 300 hours. Their operational ready rates are above 85%. Their pilots know that engine failure is unlikely. The Luftwaffe is flying Bf-109s with DB605 engines that require overhaul at 120 hours when they can get the parts. Their operational ready rates have fallen below 60%. Their pilots joke bitterly. The Allies will defeat us not with bombs, but with maintenance schedules. December 1944, Neuruppin Airfield, Germany. Oberleutnant Walter Wolfram walks around a captured P-51B that Circus Rosarius has brought for demonstration. The aircraft is coded T9 plus HK, bright yellow undersides, German crosses, painted over American stars. Wolfram is an experienced pilot with 37 victories. He has fought Spitfires, Thunderbolts, and Mustangs. Now he will fly one. The Circus Rosarius pilot, Lieutenant Klaffenbach, briefs him. The engine is straightforward, much simpler than our aircraft. Everything is consolidated. Throttle, mixture, propeller pitch, all close together. The Americans designed it so any pilot could fly it with minimal transition training. Wolfram climbs into the cockpit. Klaffenbach is right. The layout is logical. Instruments are clearly marked. Controls fall naturally to hand. After hundreds of hours in the cramped Bf-109 cockpit, the Mustang feels spacious, almost luxurious. Start sequence? Wolfram asks. Magnetos on. Fuel boost on. Throttle cracked open. Hit the starter. That is all. Wolfram follows the procedure. The Packard-Merlin fires immediately, settles into a steady rumble. He advances the throttle slightly. Response is instant. Smooth. He taxis out. The wide landing gear makes ground handling easier than he is accustomed to. Takeoff requires less attention. The Mustang simply goes. Once airborne, Wolfram begins exploring the aircraft's capabilities. Climb rate is good, not exceptional, but adequate. He reaches 4,000 meters and levels off. He advances the throttle to maximum continuous power. The engine responds without complaint. No stuttering, no hesitation, just steady, predictable power. He checks the instruments. Oil pressure steady, temperature in the green, fuel flow normal. He tries various maneuvers, tight turns, climbs, dives. The Mustang handles well throughout, and through it all, the engine never changes its tune. It simply runs. After landing, Wolfram writes his assessment. The P-51 is not superior to the Bf-109G in any single performance category. Our aircraft climbs slightly faster. Our cannon armament is heavier, but the American aircraft is easier to fly, easier to maintain, and the engine is completely reliable. A pilot can focus entirely on combat because he does not need to manage the engine. He pauses, then adds, I flew the Mustang for 1 hour. In that time, I made no engine adjustments, no mixture changes, no propeller pitch corrections. The automatic controls handled everything. Our pilots must constantly adjust throttle, mixture, and pitch to prevent engine damage. The mental workload difference is significant. That evening, Wolfram discusses his experience with other pilots over dinner. Hauptmann Gustav Sturm, a veteran with 62 victories, asks the key question. If you had to fight a long mission in enemy territory, which aircraft would you choose? Wolfram does not hesitate. The Mustang, not because it is better in combat, because I know the engine will bring me home. The other pilots nod. They all know the fear. Returning from deep penetration missions with fuel, with low damage sustained, engine temperature rising, will the DB605 make it, or will it seize 10 kilometers from friendly territory? American pilots worry about combat. German pilots worry about combat and their engines. January 1945. United States Strategic Bombing Survey. Europe. American analysts compiled data on German aircraft losses. The numbers reveal a pattern that even they find surprising. Of all Luftwaffe single-engine fighters lost between June and December 1944, approximately 37% were lost to enemy action. Another 18% to accidents, mostly landing and takeoff incidents. The remaining 45% were abandoned or destroyed on the ground due to mechanical failure or lack of fuel. Nearly half of all German fighter losses were not from combat. The analysts dig deeper. They examine Luftwaffe maintenance records captured at various airfields. The picture becomes clearer. Average time between engine failures for DB605, 83 hours under field conditions. For WWII, 91 hours. For Jumo, 213, 104 hours. Average time between engine failures for Packard-Merlin 1650 Merlin, 276 hours. But the numbers alone do not tell the full story. The analysts' interview captured German mechanics. The testimony is consistent and damning. Unteroffizier Hans Becker, mechanic with JG-27. We could not get parts. We waited weeks for cylinder assemblies, for bearings, for gaskets. So we improvised. We took parts from crashed aircraft. We used gasket material, not designed for engines. We mixed oil grades because we had no choice. The engines failed because we could not maintain them properly. Obergefreiter Ludwig Klein, mechanic with JG-53. The DB605 is a beautiful engine when new, but it requires perfect maintenance, perfect fuel, perfect oil, perfect conditions. War does not provide perfect conditions. American engines tolerate imperfection. Ours do not. Feldwebel Otto Reinhardt, mechanic with JG-300. I watched American mechanics work on captured aircraft. They changed an entire engine in half a day. Just unbolted it, lowered it out, lifted in a new one, connected everything. Done. For us, an engine change took 3 days minimum, usually longer. And we needed special tools. The Americans needed basic wrenches. The conclusion is inescapable. German engines failed not because German engineering was inferior, but because German engineering philosophy was wrong for mass warfare. Precision works beautifully in small numbers. Craft production suits specialty applications, but war consumes machines in vast quantities under terrible conditions. War needs crude reliability, not refined excellence. March 1945, Packard plant, Detroit. The production lines run 24 hours, 3 shifts, 7 days a week. Assembly workers, mostly women, build Merlin engines with practiced efficiency. Sarah Mitchell, 23 years old, installs pistons on Bank A of every engine that passes her station. She has done this job for 18 months. She can complete the task in 7 minutes. The pistons are pre-selected for weight range, but not individually matched. She installs them in order. Any piston fits any cylinder within the tolerance range. 2 stations down, her friend, Dorothy Chen, installs the crankshaft. The crankshaft arrives pre-balanced to within acceptable limits. No fine-tuning needed. Dorothy lowers it into the crankcase, installs the main bearing caps, torques the bolts to specification. 12 minutes. 4 stations further, Mary Kowalski installs the cylinder heads, pre-assembled, pre-tested, gaskets are standard, bolt pattern is standard, torque sequence is standard. 15 minutes. The entire engine assembly takes 22 hours of total labor time spread across multiple workers on a moving line. Quality control consists of systematic checks at defined intervals, not comprehensive inspection of every part. The result is an engine that is good enough by German standards, but excellent by the only standard that matters. It works. Packard produces 1,800 engines in March 1945. Rolls-Royce, Ford, UK, and the other British plants combined produce approximately 1,400. The Germans, struggling with bombed factories and material shortages, produce 950 engines of all types. The numbers tell the story. American mass production has simply overwhelmed German craft production, not through superior engineering, but through superior manufacturing philosophy. April 1945. Rechlin. The test facility is being evacuated. Allied forces are approaching from both west and east. Hartmann oversees the destruction of sensitive documents and equipment. The captured P-51B sits in Hangar 7. Hartmann walks around it one final time. This aircraft taught him more than any German prototype. It taught him that engineering is not just about making things better. It is about making things better for the conditions they will actually face. The Packard-Merlin in this aircraft has now run for 432 hours total. It has been used for testing, demonstration flights, and evaluation runs. It has been abused by pilots unfamiliar with its characteristics. It has run on German fuel, which has lower octane than specified. It has operated in winter cold and summer heat. It still runs perfectly. Hartmann's last report, written hastily in the chaos of evacuation, contains one final observation. The victor in this war was determined not in the skies, but in the factories. The nation that could build adequate machines in unlimited quantities defeated the nation that built superior machines in limited quantities. We pursued perfection. The Americans pursued sufficiency. In total war, sufficiency multiplied by scale defeats perfection constrained by complexity. He orders the Mustang destroyed. It is too valuable to leave for the advancing forces. Mechanics drain the fluids, remove critical components, place demolition charges. As Hartmann watches the hangar burn, he thinks about what could have been. If Germany had adopted American methods in 1940, if they had prioritized reliability over performance, if they had designed for mass production instead of craft production, but that would have required abandoning everything German engineering stood for, the pursuit of excellence, the pride in precision, the craftsman tradition, dating back centuries. The Americans abandoned excellence in favor of adequacy, and they won. May 1945. War's end. The statistics are compiled. The final accounting is made. Total Packard, Weitz 1650 Merlins, produced 55,051 engines. Total Daimler-Benz DB605s produced 42,400 engines, but production numbers tell only part of the story. Operational availability tells the rest. Average operational ready rate for P-51 units in Europe, 1944 to 1945, 87%. Average operational ready rate for Bf-109 units in Europe, same period, 61%. For every 10 German fighters theoretically available, only 6 could actually fly on any given day. For every 10 American fighters, nearly 9 were ready. The mathematics of attrition become simple. Even if German pilots were better, even if German aircraft were superior, they were overwhelmed by numbers they could not match because their machines would not stay in the air. July 1946, Detroit. Packard begins winding down military engine production. The war is over. The contracts are ending. Soon the production lines will return to building automobile engines. George Christopher tours the factory one last time before retiring. He passes the stations where workers assembled Merlins by the thousands. The tools are already being removed. The overhead cranes are going silent. He stops at the engine test stand. One final Merlin runs there, going through acceptance testing. He watches the needles. Oil pressure steady, temperature normal, power output within specification. How many hours on test engines? He asks the operator. This one? 6 hours so far. We'll run 8 hours total before sign-off. And the failure rate? Last month? 0.8%. 0.7 the month before. Christopher nods. When they started in 1941, failure rate was nearly 20%. They brought it down through relentless focus on process improvement, quality control, and operator training. The Germans never got their failure rate below 8%, not because their engineers were less skilled, but because their system could not support consistent quality at scale. Good work, Christopher tells the operator. He means it. This operator, this test stand, this entire factory represents a triumph not of engineering genius, but of industrial organization. The Americans did not build a better engine through brilliant design. They built a better engine through better manufacturing. They won not with innovation, but with implementation. As Christopher leaves the factory for the last time, he passes a wall where someone has posted a quote. He stops to read it. The superior man understands what is right. The inferior man understands what will sell. Confucius. Someone has added a handwritten note below. In war, the superior nation understands what will work. The inferior nation understands what is perfect. Christopher smiles. Crude philosophy, perhaps, but true. 1948, West Germany. The Bundeswehr begins reforming. They need aircraft engines. American surplus is available, including Packard-Merlins. German mechanics, veterans of the Luftwaffe, begin maintaining these engines. Among them is Ernst Müller, the mechanic who first examined the captured P-51 at Rechlin. Müller trains new mechanics on the Merlin. He teaches them American methods, torque specifications instead of feel, replacement instead of repair, standardization instead of customization. One young mechanic, fresh from technical school, complains. This is not proper engineering. The tolerances are too loose. The parts are not precision-fitted. Müller looks at him for a long moment. Then he says, I maintained DB605 engines for 3 years during the war. I was good at it. I knew every trick, every shortcut, every way to coax more life out of a worn engine. And still, half our aircraft were grounded at any time because engines failed. He gestures at the Merlin on the stand. This engine, which you call improperly engineered, will run 300 hours without major attention. Your beloved DB605 needed constant care to reach 120 hours. So tell me, which is proper engineering? The engine that requires an expert to maintain, or the engine that runs despite inexpert maintenance? The young mechanic has no answer. Müller continues more gently. German engineering is not wrong. It is brilliant. But it is brilliant for a world that no longer exists, a world of skilled craftsmen and abundant time. War taught us that adequacy in abundance defeats excellence in scarcity. The Americans understood this. We did not. It cost us everything. 1967, Detroit. The last Packard-Merlin is removed from service. Air racing is its final duty. Modified beyond recognition, boosted to over 2,000 horsepower, it still runs reliably. Some of these engines have logged over 8,000 hours. They have been rebuilt multiple times, but the basic block, the core design, remains the same as 1941. A German DB605 rarely saw 1,000 hours total life, including rebuilds. The difference was never in sophistication. It was in philosophy. Today, scattered across the world, dozens of Packard-Merlins still fly, in restored P-51 Mustangs, at air shows, in vintage racing aircraft, in museums where they are occasionally run. For demonstration, they start reliably, they run smoothly, they require minimal attention. DB605 engines exist in museums too. Beautiful machines, testaments to German engineering excellence, but few run. They are too complex, too delicate, too difficult to maintain without the infrastructure that supported them. The lesson of the Packard-Merlin is not that American engineers were smarter than German engineers. They were not. German engineers were brilliant. The lesson is that intelligence must be applied correctly. The Germans applied their intelligence to making engines better, The Americans applied their intelligence to making engines work. Better is the enemy of good enough when good enough comes in unlimited quantities. The Packard-Merlin was not the best engine of World War II. On paper, it lost to several German designs in specific performance categories, but it was the most effective engine because effectiveness is not about specifications. It is about availability. A 300-hour engine that is available wins against a 200-hour engine that is not. A crude engine that mechanics can repair in the field wins against a refined engine that requires factory overhaul. An adequate engine produced by the thousands wins against a superior engine produced by the hundreds. Klaus Hartmann understood this in June 1944 when he first examined the captured Mustang's engine. He wrote reports, he made recommendations, he explained the American advantage in terms any engineer could understand. But understanding came too late. Germany had committed to a path in the 1920s and 1930s. Precision engineering, craft production, excellence in every component. That philosophy built Mercedes-Benz automobiles and Zeiss optics and Leica cameras. It could not build 50,000 war-winning engines. America committed to a different path. Henry Ford's assembly line, interchangeable parts, mass production. That philosophy built mediocre products in vast quantities. In peace, German methods produced better results. In war, American methods produced victory. The Packard 1650 Merlin was not a great engine. It was a good enough engine, available in unlimited quantities, maintainable by ordinary mechanics, reliable under terrible conditions. That was enough. Klaus Hartmann, had he survived the war, would have understood. The Americans did not defeat Germany with better engines. They defeated Germany with more engines that actually ran. 300 hours between overhauls does not sound impressive until you compare it to 120 hours. Then it is revolutionary. The Germans looked at the Packard-Merlin and saw crude tolerances, rough castings, unbalanced components. They saw everything it was not. They failed to see what it was available. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.